So today I would like to convince you to look at AI from this deep generative modeling perspective. And before we start, of course, a little bit of advertising my little baby. So this newly published book, Deep Generative Modeling. So it's available, and also a lot of materials included in this book are presented in the blog here that I have. And yeah, let's start. So I would like to start with a very easy question. So what is intelligence, right? Now we can probably spend hours on discussing what is intelligence. And actually, we are artificial intelligence scientists, researchers, engineers. So maybe it's easier for us to think about what is artificial intelligence instead, right? And this we can more or less define. And this is pretty important to, of course, first ask this question of this artificial intelligence before we even start talking about deep generative modeling. And when we talk about artificial intelligence, we definitely need to mention something about environment, right? So every artificial intelligence system, either it is an app on our phone, smartphone, or is it a robot in some form, it interacts with environment. That's why it's intelligence in some way. And when we have this artificial intelligence system, right? So as I said, it interacts with the environment. So it makes some decisions, takes some actions, and then it observes through some sensors and looks at the information coming back, right? And so this is, I think, the simplest possible system, or in general, something like AI system environment. And this is not necessarily about reinforcement learning, because this diagram you probably see when you talk about reinforcement learning, but this is, I think, in general, what is artificial intelligence? We need to mention that there is this agent, some robot maybe, or some AI system, and some environment. And what is important here is this word information, right? So this information, for instance, in terms of bits or in any other form, comes back to this AI system. So when we talk about artificial intelligence, we have to consider some very closely related topics, right? Information processing. So how this sensory data, raw data coming in, how we can process that, or maybe already processed information, how we can process it. Then how we can store it, right? In some maybe efficient or way, or maybe some other way. And next, how also to transmit this information. So for instance, to another agent, or so to another AI system, some app, how they communicate, right? How to efficiently send this information. And so the next, of course, topic is obviously decision making. But I make this distinction very clear that actually this all things about processing, storing, transmitting, this is extremely important. Decision making is important as well, but we need to keep in mind these different concepts. These are about artificial intelligence. And if you look at these topics, right? So for instance, information theory engineers would say that, oh, this is our field. But in AI, we actually take these concepts and we a little bit relabel them, or we take a couple of them as a mix and we use it for instance, we say about learning. When we say about learning, we talk about some kind of storing. We need to store it in some sense. We call them some knowledge representation or some models, right? This all kind of things. So they are inherited from other fields or actually relabeled in artificial intelligence, right? But these are these core concepts that are so important when we talk about artificial intelligence. Of course, I don't want to spend time now and discuss how to define artificial intelligence. I just want to throw some concepts that we need to be aware of when we talk about artificial intelligence. And now let's say that more or less we know what is artificial intelligence, about doing something with information in some form and making decisions. So how we can formalize the problem of AI. And now in the next slides, I would like to very briefly define this problem of artificial intelligence, and then I can move to deep generative modeling and how these two things interact. So before we go to how to formalize artificial intelligence, I want to very briefly go through information theory. So what is information, right? So Claude Shannon said that if we have a random source of data, we can somehow quantify uncertainty of this source of data by calculating something that is called the entropy, right? And the entropy is maximal when all possible pieces of this information from this source are equiprobable, right? So in other words, if every single state is equiprobable, it has the same probability, the uncertainty is largest, right? The largest. And the minimal of entropy is when one value is certain. So from all states, one state will always be on, right? So will be observed, for instance. So then there is no uncertainty, there's full certainty, right? So this is the entropy, is something like the main force behind the whole information theory, right? This concept. And another thing is that optimal message length is more or less the entropy, right? And in general, the information theory focuses on transmitting information, right? And this is defined through these lenses. So how to transmit properly information, okay? But also, of course, about storing information. Another concept is joint entropy. When we have two sources of data, we can still define entropy. And we have also the conditional entropy. And the difference is that in the conditional entropy, we calculate the expected value with respect to both states. So we need to sample, in some sense, all possible states. And then we just are interested in this conditional logarithm of the conditional distribution. And so this is how we can quantify uncertainty. And there's another concept that will play the crucial role in this talk, is mutual information. So we have two sources of data. Let's say, I know, snapshots, images of environment, and this is X, and Y is a decision that we make, okay? And now the mutual information quantifies how much information is shared by these two sources, okay, of data. So, and this is defined as the difference between the marginal entropy and conditional entropy, okay? And why this concept is so useful? Because it says when I observe, for instance, I take a snapshot of my real world and I need to take some action. I'm in a maze and I see that the left part of my image is open and the right part is a wall. Then, of course, there is a shared information because my action will be I go to the left, right? And so, in other words, mutual information tells us how much knowing one source of data reduces uncertainty about the other one. Again, if I have this image or I have no image, my eyes are closed, probably going left and right doesn't matter if I observe something or not because my eyes are closed. But if I open my eyes and I see that, oh, actually to the left is open, definitely it reduces my uncertainty, right, about the worlds. So now keep this in mind, and we can now define the problem of artificial intelligence, broadly speaking. So let's say that we have these two sources of data. We have observations of our world in terms of, for instance, images, and we also take some actions, make some decisions, okay? So now, additionally, we also need some kind of a model because, again, we go back to this original diagram. We have the environment, so these are X's and Y's. Environment generates these two. And then we have a model that is our, let's say, AI system, right? So this is some kind of representation of this world. And the problem of AI would be then the following: just maximize the mutual information between the real world, X and Y, and the model, right? So if we go back, so the mutual information tells us how much knowing one random variable reduces uncertainty about the other random variable. So in this world, in this case, we just want to maximize the mutual information between the world and the model, right? Because we want that these two random variables share as much information as possible. Or in other words, if we have a very good model of the world, knowing this model will gives us all possible information about the world. So it reduces completely the uncertainty. So if we now look at the definition of the mutual information, we have this entropy of the world. So this is something that, what is the stochasticity in the world? I have no influence on that, right? Or almost no influence on that. So I can't do much about it. But if I have the conditional entropy between the world for a given model, right? So if I want to find a model that is best in this scenario, so this is the quantity we want to optimize, because this is the real goal. Because if this conditional entropy, right? If for a given model I know precisely what to do, this is the trick. This is what we should do, right? We have this minus here. So if we rewrite it, so the goal is now, if we want to maximize the mutual information between the world and the model, so this is equivalent to minimize the entropy, right? The conditional entropy. Here is actually minus missing here in front of this H. So if we write it down, so the conditional entropy is just the expected value with respect to all these variables. And then we can factorize. We have logarithm of P of Y given X given model and log of P of X given model, right? So just standard rules of probability theory. So what we have here, so let's say you have to believe me, right? That this is, let's say that I'm correct. And this is the true goal of AI. But it serves as a very good purpose. So it tells us that if we want to look at the AI, we should consider a model for decision making, right? So this is a model that if I know X and my model of the world, I can take some actions. So I know this distribution. And also, if I know the model, I know what will happen in the world, right? So this is a model for, I call it understanding the world, the surrounding, the environment, right? So these are something like, now we are getting into something very, let's say, tangible, right? So we have the goal of AI is actually to make a model about decision making and make a model about understanding. So this is something that I think we all agree with, right? But here we see that actually it follows from the information theory in some sense. So we need to have these models, two models for decision making and understanding the world. And this is precisely what generative modeling says. So if you want to create some model of reality, you should think of it in sense of from the generative perspective. And probably we as human beings, I can even hypothesize that we actually do something like that in our heads. If I want to achieve some goal, I'm not just doing this step by step, but I probably think of the whole sequence of actions and I predict what may happen. So if I want to go out from the building, I need to go to the elevator, click a button, wait for it, go down, and I can imagine exactly every single step, right? And that can help me to plan everything, okay? However, nowadays in AI, we are mainly focused on decision making part, right? If we go to deep learning, so a bulk of work is on making decisions. So the standard thing is that, for instance, image recognition or image classification. So we can have very nicely trained model. But it turns out that if we add a little bit of noise to this image, and this image on the right is really it is just added the same image on the left, but just with some Gaussian noise. To us human beings, we don't see any difference. But a neural network that is trained could give us completely different and wrong answer, okay? And it fails completely. And why? Well, we will see in a second why. And another example that is pretty recent. So there was this OpenAI clip model that was able to generate images or classify images based on image and text. And Stanislav Ford made a very nice blog post where he described how to attack this model, right? So for a while, a lot of people were excited about this clip model, but it's still this rather classification model rather than fully a model that fully understands what's going on. And for instance, there is some image, it is properly classified by this clip model, but if you add a label with handwritten word bird, suddenly the model starts classifying this as birds. Okay, so it's already something like a little bit weird. And then if you add some adversarial attack, suddenly it classifies it as frog. So it shows that we completely miss a lot of stuff in AI. We still don't understand what we are doing, basically, and we are a little bit over excited about it. But the question is why it happens, right? So my understanding is the following, that if we imagine now very simple example, we have two clusters of points, and there are orange triangles and blue rectangles. And so now if we want to classify this cross, right, black cross, we can say the following. If we train a model, in this case, I trained a naive Bayes model, right? We have a very nice linearly separable clusters. And we can say whatever is on the left is orange, whatever is on the right is blue, right? So what is the classification of this? What is the class of this the cross? Definitely with high probability, it's blue because it's far away from the decision boundary. It's definitely blue. But is it really true, right? Imagine now that this orange and blue points, they represent, for instance, a robot walking around and taking some action. So taking, for instance, first taking photos of the environment, right? And it puts somewhere this in its internal representation. Is it really blue? It is really far away from this blue cluster, right? So maybe our model shouldn't be very certain about this, that this is really blue. The situation is completely different if we consider the joint distribution, okay? Because now the joint distribution will tell us the following. Of course, the P of y given x, so this cross is maybe with high probability, with high certainty, it's blue. But because P of x now will tell us, wait a second, this cross is far away from this cluster of points, is far away from this cluster of points. So probability of this cross is actually very low. In other words, if we trained on these data points, this probability would tell us that, wait, I have never seen this object before. This is something like completely different. Maybe now we went with our robot from Amsterdam to Abu Dhabi, for instance, where there's a lot of sand, unfortunately. In Amsterdam, not always we have this weather. So it will be completely different for our robot. So then it will say, whoa, well, wait a second. It is something new. I have never been here. The probability of environment is, for me, very low. So if we multiply these two distributions together, the joint distribution will be very low. So this will be actually uncertain decision under these circumstances. And to me, this is the deep generative modeling idea. This is the idea that connects us also to the goal of AI. We need both models, right? Not one separately, both models together to achieve the higher level of AI. So now this P of y given x, we basically know how to learn it. We have the whole field of deep learning. We have random forest, so machine learning. We know more or less how to create these models. The question now is, and this is what we cover today, is how to model this P of x. So this P of x this distribution over this marginal over states of the environment, let's say, it's now we can put it under the umbrella term of deep generative modeling. And we have a few classes. So autoregressive models, flow-based models, latent variable models, where we distinguish between, for instance, GANs and VAEs and diffusion models. And we have also energy-based models, right? They have some pros and cons. In general, autoregressive models, flow-based models, and they can calculate the exact value of the likelihood function. However, they are typically rather slow, and not always they can provide some internal representation. So they cannot be so easily used for instance, classification, but they can be used anyway. But they have also stable training. Similarly, prescribed models and energy-based models, they have stable training, but the likelihood function is either approximate for prescribed models or unnormalized for energy-based models. So not always we can so nicely calculate the joint distribution, you know. We can have some sampling fast or slow and so on. And for implicit models, for GANs, for instance, the training is rather unstable. Likelihood is not available. Sampling is very fast and probably with very high quality, and also representation not necessarily we can use. But so, of course, as you know, as usual, also in life, there are always some pros and cons. Depending on your application, we can, you know, juggle these models and we can use ones or others. And in general, how we can use these deep generative models. So typical applications are like text synthesis. So we can really create this, you know, impression that when we have a chatbot, we are talking with a human being, not necessarily only with some machine that always answers in the same way. There's always a little bit of stochasticity, so the texts are different. For images and audio, so we have, for instance, this speech synthesis, image synthesis, also deep fakes that you probably have heard about a lot. They are, you know, definitely created by deep generative models, plus some additional maybe techniques to improve the quality, but this is definitely true. Also, deep generative models were used or have been used for video games to go from lower quality video games from 90s or 2000s to improve the quality, to, you know, generate missing details and so on, so on. Recent very sexy field these days is molecular dynamics, drug discovery, and deep generative models are, you know, on top of these applications. We'll discuss it a little bit in the very end. And overall, you know, we can use deep generative models for active learning, reinforcement learning, medical imaging, and so on, so on. So in many applications, basically, as I try to, you know, convince you here today, we can use it anywhere where we want to use AI, right? And so, what are the basic rules for deep generative models? It's very simple. It's about probability theory. So we have the sum rule that we can calculate the marginal distribution, or the product rule that we can express the joint distribution in one particular way. And here I try to convince you that the second way is the better one, because we have decision making and world of the environment. Okay. The objective function in our case, most of these cases, is the log likelihood function, and the log likelihood function is just assuming the IID that our data counts independently and from the same distribution, is just applying the expressing the joint distribution of the data as a product of individuals, and then applying the logarithm, so changing product to sum of logarithms. And of course, we have very limited time, and I also not giving you a lecture, but I just want to, you know, show you a couple of things. and convince you to use deep generative models. So today I will really focus on flow-based models a little bit and prescribed models, and give you some examples later on at the end. So let's start with flow-based models. Flow-based models are very nice models from two perspectives. First, they are deeply rooted in the probability theory. So this is actually nice because we can have some very nice principles. And second, they actually made a huge step, or they put deep generative models into the first class of this, or the mainstream of deep learning. And so what are these flow-based models? So the idea is, maybe before I talk about this expression, the idea is to use the change of variables in statistics or probability theory. But the idea is pretty simple. Let's say that we have on the right, we have some very fancy, very weird distribution that we cannot even analytically express. Okay, it's something like multimodal. We don't know it's Gaussian or not. Who knows? It's very complicated. We can think of pixel space, and then the idea behind flows is that if we apply an invertible transformation, so if I go from one object to the other and I go back, also called bijection, if I can formulate such a transformation, then I can transform this multimodal distribution by applying multiple times, maybe some invertible functions. I can represent it as a simple Gaussian, right? And if you are not familiar with flows, at the first sight, you can say, "Whoa, this is something like magic." But imagine that you have a pile of sand, okay? And this pile of sand is really like a nice pile. It looks like a Gaussian, right? And now imagine that my hands are these transformations, these functions f, okay? So first I can cut it in half and move to the right and to the left. Now I have two piles of sands. Then I can do the same with these other piles. And I can just divide them so and so and so forever. And at some point, if I stop, so it's not anymore forever, but you know what I mean. So I will have some very weird, this sand is distributed in a very weird way. But if I record everything, all my moves of my hands, and now I play it backwards, so now you will see that suddenly all these piles, they will start moving together, and eventually I will get my nice Gaussian of sand, okay? So this is the idea behind it. And mathematically speaking, is that every single distribution I can express as something that's called base distribution. So for instance, a Gaussian, standard Gaussian, where the standard Gaussian random variable is just the inversion of this transformation of the complicated x. And because during these transformations, I can change something that is called volume of this by applying this function f, I need to normalize this distribution so that it sums to 1 by something that's called determinant of the Jacobian, okay? And we go, so the principle is that we go from the complex distribution to the simple distribution. Then we have this base distribution is known. And the tricky part is this Jacobian that must be tractable. Jacobian is just the first derivatives across all dimensions of this function f. Of course, this is bijection, so it must be invertible. So this dimensionality of x and dimensionality of z is exactly the same. If I have 1000 pixels, z is also 1000, okay? And there are two tricks. The first trick is that we need to ensure that the transformation is invertible, right? Invertible, we need to have invertible neural nets. And second, we need to have nicely computable, tractable Jacobian, okay? And the training objective, because I talked about the log likelihood function, so it's very nice because if we apply the logarithm here, So I have the logarithm of the base distribution minus, because this -1 goes here, of the sum of the logarithms. So I sum the logarithm of the Jacobian determinants per layer from these old transformations. So it's actually not difficult to implement if you think about it. And the question is, can we nicely define these invertible transformations? It turns out that actually invertible neural networks is not something like a big thing. We can quite easily do it. The problem is to calculate this Jacobian. And in 2016, if I'm not mistaken, there was a paper called Real NVP, non-volume preserving flows, and they designed this neural network in such a way that we take the input, we cut it in half, and one half is unprocessed, and the other half is processed in this very nice way, okay, just by processing the first part here. By design, this is invertible, okay? If you do the simple math, you will see that this is invertible. And also then we need another component, it's called permutation layer, that we just simply flip it. And what is cool about it is that the Jacobian of this transformation is tractable, okay? So how does it work in practice? It works very well. This is a paper from 2018 from OpenAI, from Diderot Kingma and Prafula Dariwal. And they were able to train such a model, and they were able to generate these faces. Please remember, this was 4 years ago, and still the quality of that is pretty good, okay? So, of course, we see that these are fakes, like, for instance, this background is a little bit off, but if we look at maybe some teeth, but overall, it was like a big breakthrough, because this was the first paper, and these images are of high quality, okay? So high resolution, I mean. So these are these big images. And this was the first paper that used principles, of probability theory, and was able, without any other tricks, to train such high quality model and to generate such high quality images, okay? So this was something that these two guys, they showed, hi, this is our model, we can do that, okay? And this was a big breakthrough. It shows that actually the log likelihood function is perfectly fine to generate such images. All right. So now the second part, second model, this is actually one of, I think, my favorite class of models, so-called prescribed models like VAEs. And what these models are about? These models are about latent variable models. And they are perfectly suited to explain also this generative perspective, okay? So imagine that we have these high dimensional objects, for instance, like horses, okay? And we have photos of horses. And we can imagine such question: how to generate these images? One can say, all right, so if I want to generate a brown horse that is huge and stands on the grass, so these are already some low dimensional, highly abstract concepts like height of a horse, color, maybe background, and so on, right? So in some sense, we can say there are some latent, hidden factors in data, these latent variables, that if I know them, I can actually generate details, and this will be the final photo, right? And this is precisely this idea. This is this very generative process that first imagine what kind of concepts are there at the high level, and then generate this final object that we want. And typically these latent variables are lower dimensional, right? And they create these low dimensional manifolds. Because so here we have like 3D space, but this low dimensional manifold is 2D. It's like a piece of paper just folded a little bit. So it's 2-dimensional, but it's embedded in this 3D. right? So this is the general idea. And because we have some prior distribution, we can call it, or marginal distribution over latent variables Z here, we also have this conditional distribution of X given Z. So what about our objective function? It's still the log likelihood function, but now, of course, we cannot calculate the log likelihood function for both X and Z because these are unobservable, they are latent. So the probability theory tells us that if you have latent variables, just get rid of them, sum them out. And this is exactly what we need to do. So we need to calculate here, because we talk about maybe continuous variables, so we calculate the integral of the joint distribution that is factorized in this way, right? So far, so good. But what's the problem then? Well, this integral is intractable. If we have P of Z is a Gaussian, P of X given Z is Gaussian, and the dependency between Z and X is linear, then we can calculate this integral, and the resulting model is the principal component analysis. But if we only change the linearity to non-linearity, the dependency between Z and X is non-linear, we cannot calculate it analytically anymore. And if we take P and this P of Z and P of X given Z, some other distributions, we can't do that anymore. So it sucks, right? So we need to think of something else. The one approach that could be applied here is applying the variational inference that results in something that's called variational auto-encoders. And by introducing an auxiliary class of distributions Q of Z given X, right? So from the other sides, or from X to Z, we can lower bound the log likelihood function. And since we maximize log likelihood function, we maximize the lower bound. So this is perfectly fine. And it actually, if we do a little bit of math, I skipped it because of the lack of time. But so we end up with this elbow, so-called evidence lower bound. And we have here, like we go from X to Z and then from Z to X. So this is very often referred to as the reconstruction error. And we have this naturally arising regularizer, that this is a difference between actually the Kullback-Leibler between the Q distribution and the prior, okay? Here we consider something that's called amortized inference. It means that we have one single, for instance, neural network that takes X and returns parameters of this distribution, for instance, Gaussian. And we also use so-called the reparametrization trick that, for instance, instead of just sampling from these distributions, it is enough if we take a neural network, it returns mean and standard deviation, and then the only stochasticity comes from the auxiliary source of randomness. This is, for instance, standard Gaussian. Because of lack of time, I cannot delve into details, but these are two concepts that must be remembered from this slide about variational autoencoders. These are two components that are so important for VAEs, okay? And why we use the reparametrization trick? Because it reduces the variance of the gradients, okay? And that's the point. All right, so how it works in practice. So here a little bit of bragging about my own project together with my really brilliant master student, Yannis Gatopoulos. So here we propose, and this is also a very good example why I love VAEs, because they are extremely flexible, okay? And here is a hierarchical model of VAE that from X we get Y, that is, for instance, downscaled image. That's why you can see that maybe this is there are some blocking effects because it's downscaled. And then there are two levels of latent variables. And so why this is interesting, because we did with this downscaling, and then we can generate that. First you generate some low quality image, then you generate a better quality image, and then you generate the high quality image. And this is exactly this process. So as you can see, it works as we expected. And another transformation that we used was first generate sketches and then add colors. And we imagine something like, maybe when I want to paint something, so first I use my pencil and then I put colors. And this, again, it worked precisely in this way. Another model that is very important, another hierarchical VAE, is so-called top-down variational autoencoder. And this is from OpenAI. You can see the quality is better because, of course, in academia, we don't have maybe enough resources, but in OpenAI, they had a lot of tons of VAEs. And you see that actually they generated so naturally looking faces. All of these are fakes. They are completely generated, but we can be very easily fooled by them. They really represent some living people. And very recently, there is a follow-up on this work from 2015, so-called diffusion-based deep generative models. And they have a lot of successes. They're extremely popular these days, especially in Google. And the idea is that we have very deep VAE that doesn't change the dimensionality. And in so-called forward diffusion, so the variational part is fixed. It is defined like this. We have these betas, and we just take the previous model as the mean, and we add some variance. So it's in some sense we are like adding noise to image, so that at the end we have almost like pure noise. And then we train the so-called backward diffusion, so decoder, in such a way that it gives us, we can generate back. Right. So again, about this model, so you can take a look at my book, and you can read about these various models in the various chapters. And what about some applications? At the very end, I would like to end up with a few applications that you may find interesting. One application that I find extremely interesting and important is neural compression. So in general, this compression scheme is that we have original image, we transform it somehow, we transform it into signal, discrete signal, we have entropy coding, then we have a bit stream, and then we decode everything back. If we take JPEG, so of course we use this discrete cosine transform and some quantizer, and we invert it. And we can, of course, also use neural nets for that. So we can use a neural network to process this image, use some kind of learnable quantizer, and then use a distribution that will be used for entropy coding. And it's the same model will be used for entropy decoding. Where then this deep generative modeling comes into the game? Well, these little fellows. So if we want to encode the discretized symbols, we can use flows or autoregressive models. And we can use that for entropy coding. So very, very important. Okay, so you can see that actually deep generative modeling could be a part of, for instance, such scheme. Another very beautiful example from last year from DeepMind, and to me, it's one of my favorite papers that somehow went without a lot of fuss, to be honest. But this is about molecular modeling. So the model was, again, VAE, so there was encoder and decoder, and they had very noisy observed images from cryo-EM. They were encoded them, they encoded them in the latent space, then decoded them into 3D. So there was like intermediary level that from this 2D, they generated 3D structure, and they had some physics-based model that from this 3D structure generated something like noiseless version of this image. And so then they calculated the loss function. Okay, so neural network decoder, the renderer was fixed. Another example from Microsoft from 2 years ago, 3 years ago, very similar VAE encoder, then some set of differential equations were used to generate signals, then a learnable function of distribution for adding noise. So this we can use for genetics. Okay, I do on purpose now throw some completely different applications because these are still deep generative models with some very nice properties that there are some added values, like some maybe simulators. Okay. And the last example from last year about robot learning, so some multi-fingered grasping robots. There was a generative model constructed for generating trajectories, what to do next, right? in the space. They had a simulator, and then they had a physical robot, and they used both data to actually learn a model. Okay, there are tons of other interesting models, like in reinforcement learning. There are these world models that an agent has an internal representation of the world, and then it moves. Okay, so again, advertisement. So if you're interested in this topic, please take a look at my model, my book of where you can read about these models more. And to conclude, so why generative modeling? Because we want to make decisions and we want to know the world. How to model this joint? Distribution? There is a class of approaches called hybrid modeling. I skipped them here, but they are definitely very interesting. And some important directions. So in my opinion, better uncertainty quantification. So this is something that if a robot can walk around and can say, oh, I am uncertain, I need to talk with my human manipulator, this is what we need, right? We need to communicate. When we talk to each other, especially, for instance, as scientists, we want to talk about something that is uncertain because we don't know about it. So we need to communicate. Without knowing what is uncertain, we don't know what to talk about. We definitely need new parameterizations of these models. So I explained you very, at this conceptual level, this not very specific, right? What kind of architectures to use? We definitely need to look into that as well. Another problem is out of distribution. We need to know when, like in this example in the beginning, this big black cross, when I can say that this is out of distribution, when I can say that this is something weird and new. Why we need this out of distribution? Because we need to eventually propose continual learning, something that we can learn continually, like we human beings, like animals, maybe even insects, but maybe here I'm a little bit too far, but let's say animals, we know what to do next with new data. We are not forgetting everything, but to know that, we need to know what is new, what is out of distribution, that I can, for instance, update, right? So that's it. So thank you very much. I'm almost on time. If we could also the beginning. So yes, I'm now open to questions.
Okay, thank you, Jakub. That was very interesting. Topic and maybe future work as well.
Yes, definitely.
Yeah, there are many questions, maybe from someone, like he made most of the questions. I don't know if you can see them, but I will try to summarize. So there is, I think it's an easy question about GAN is black magic. And everyone is using GAN to do improving their models or generating new data. So can you elaborate on how the mathematical modeling, the one that you showed, actually helped us understand it's not a black magic anymore?
Yes.
This is one big question. I think it's like many lines.
Yes. So, and this is actually a very good question because, so for instance, and don't get me wrong, so I'm not a big enthusiast of GANs, but it's not because they are bad. On the contrary, they are very good, but they are not necessarily, I don't necessarily believe in these adversarial losses. So when I mentioned this log likelihood function, this is something that naturally occurs or follows from principles of probability theory, right? So this is something that from statistics. And so that's why, when we have some very principled manner of expressing the world, probably this is something good, right? And this is also, to me, after this is some years that I work on these topics. So to me, everything is actually, I see that everything follows the same principles. And that's why I love these models. And this is why this is so useful, because we have actually, in fact, if you think about it, there are some a few principles that you need to understand very well. and then everything is like unified one language to represent reality. And that's why this is so useful. That's why this principled way of expressing reality is so useful. And for instance, GANs are indeed, and also I would say that these models, to me, of course, there are black boxes because we use neural networks there, and we still not understand fully neural networks. But at least they are not, to me, fully black boxes because I have the rules of probability theory, so I at least understand what I'm doing, right? And so
yeah, actually, that's very so this is actually a question from Elcio Ferranti, if I mentioned his name correct. So there is another question in the beginning that it did not come. Ghosty Epain. He asked about slide number 13. You actually divided, I mean, the steps in developing. Yeah, there are many slides.
Yeah,
the intelligence. So he's wondering, where is Ghosty? Where is the perception, or where is the perception within that context?
Right. Okay. Very good question, actually. So obviously, when I created these slides, I also created them to support my let's say the story. But I would say that this information processing, we can, or this transmission, so we can say that it is there. So it's something that I need to, of course, receive some information. So that's why also here I included that this arrow. This is so important, right? So in some sense, this is like when I transmit, I also receive, and when I send or I receive, I also need to process it somehow. So we can say, of course, that in some sense, this is like combined, this is covered here. But obviously, this is like when we have a robot, we need to have also some camera or maybe some other sensor, like I don't know, some waves to record radio waves or something, whatever. Or some touching sensors and so on. So this is definitely extremely important. Yeah, I can be the smart ass and I can say now, oh, this is actually covered by information processing and information transmission.
Okay.
It's somewhere there.
I don't see any, like, if there is any question, if you wanna raise your hand as well. Oh, we have one more. I think we will.
Yeah.
So someone from Quantum Algorithms Group.
All right.
Leonardo.
Yeah, I know.
Leonardo. So he's saying, can you comment on the flows for discrete distribution? I want to know more about how the discrete distribution not have. The Jacobian one can, of course, it's very long, lengthy.
Yes, I read it. Yeah,
okay.
I read it. So yeah, so this is actually very, very interesting point. So there is a model that is called invertible discrete flow. However, I think the name integer discrete flow. Sorry, integer discrete flow. However, it sounds like, you know, how in Polish we say something like mashed potato or something like that. It's potato with potato. It's integer discrete. It's the same, but in some sense, of course. But there is this class of integer discrete flows, and they are invertible. And indeed, because this is discrete, so there is no change of volume. So there's no Jacobian. Jacobian is simply one. And it turns out that it is still useful. There is a paper that is called Integer Discrete Flow ++ or IDF++ from Google. And they have even very nice, let's say, small theorem or proposition, how to call it, that they show that you can learn some correlations among discrete variables, even with these invertible transformations. So in other words, if you have infinite space. So that's why integers they use. And if you have some blocks, let's imagine that we have some small blocks, they represent integers, right? So you can, this integer discrete flow, it is in some sense like moving around these blocks, okay? And then if you want to decorrelate, for instance, so you can actually, because you have infinite space, you can move to the left and to the right, up and down. So you can start moving these blocks, and then you can reorder them in such a way that you will get nicely, for instance, separable values. Like, I don't know, if you have original pixels, so then you can start changing these values in such a way that you learn something useful. Okay, so this is the, yeah, okay, cool, thanks, yeah.
That's cool. So the last question from Jonas Ickman. I think he's referring to the transformers and how, like, maybe big models, instead of using math, could actually like formulate even generative models better. So can you elaborate on that? Like, people shy away from maths or approaches and try to do complex things.
So so the answer is, of course, definitely. So transformers are used also, and the funny part is that actually, if anyone uses this for NLP or something, so we are using math anyway, but in this hidden form. So for instance, when we have any model, deep learning model, transformers included, if we train some model for NLP, so for instance, we want to predict, for instance, what is the next word, and this could be given by softmax over some dictionary, right? And actually, if you think about it, this is, and then we train it using some cross entropy laws or something like that, right? But actually, all these concepts like softmax, so we have a categorical distribution over words or characters, and now we so this is categorical distribution. So this is just a distribution. In my words, or in these words here, this slide, this is P of X. And now we have some autoregressive model that I skipped today, but you have an autoregressive model, and you have one single model that predicts, for given previous words, I predict what is the next word, right? And so this is like a neural network that we use. But again, eventually, if you use the cross entropy, you are following the log likelihood principle. You are using the log likelihood objective, for instance. And so, and definitely, so transformers, these visual transformers, we still need new kind of architectures in deep learning to properly model these distributions. And that's the whole beauty of these deep generative models, that these two words, probability theory and deep learning, they come together. And the probability theory fits it with principles, and deep learning gives this, new, very fancy, very powerful models like architectures to properly parameterize these distributions. And that's why this is so cool and interesting.